In all of these types of particles for dark matter annihilation. But the trick is that positrons and electrons, antiprotons and protons all have electric charge. So where they came from gets scrambled by the galactic magnetic field. Neutrinos don't have electric charge, but they're weakly interacting, so they're very difficult to detect. But gamma rays don't have electric charge, but are easy to detect. So those are kind of privileged messengers. They're not deflected by magnetic fields, so they point back to their source, and we know good targets to look for in the universe where there might be large amounts of dark matter. So some of those targets are the center of our own galaxy. So this is an image in radio of the galactic center region. There's a lot of stuff going on in the galactic center region, but that's also where the dark matter density should be highest. So you should have a high flux of gamma rays, but also a huge background from electrician sources. There's satellite galaxies of the Milky Way galaxy, what we call dwarf galaxies. So these are small galaxies that orbit the Milky Way that have a surprisingly large mass given the amount of stars in them. And these are old stars, so we don't expect any astrophysical background. But they're relatively far away, so we don't expect a very large flux of gamma rays from dark matter. And then going further away, there are clusters of galaxies which contain a huge amount of dark matter, but they're relatively far away from us. And they might have other ways of producing gamma rays, so they have a high background. And then lastly, the way we think structure forms in the universe is from small scales towards larger scales. So within our own galaxy, there may be small clumps of dark matter still, and if there happen to be one nearby, we might see gamma rays coming directly from that random cell halo of dark matter, even though we don't see any signal in any other wavelength. So just to wrap up, Veritas can look for gamma rays from these various classes of high-density dark matter in the galactic center, galaxy clusters, dwarf galaxies, and subhalos. And we're hard at work on doing that. So in the galactic center region, this is a map that Veritas has made of gamma rays from the center of our own galaxy. And you can see there's a very bright source right at the center of the galaxy. When that was first discovered in 2004, people were very excited. Could this be dark matter? But unfortunately, the properties of that source don't seem consistent with dark matter. It seems like there's some kind of astrophysical source at the galactic center, some kind of particle accelerator at the center of our galaxy that's producing these gamma rays. But we can look at regions away from that astrophysical source and the halo of the galactic center and search for dark matter where it still has a fairly high density. So we're working on that now. Some nearby galaxy clusters that we've looked at have let us set limits on dark matter. Again, no dark matter signal seen, so we have upper limits on what the cross-section might be. And then we really spend a lot of time looking at these nearby dwarf galaxies. And again, this is a plot of the cross-section as a function of mass of the particles. And this band is meant to show where we expect the dark matter from theory is likely to be. You can see we're setting upper limits that are still away from that. So we need more sensitive telescopes and longer observations to push these upper limits down into this band and see if we can detect dark matter. So to summarize, we've got three ways of searching for dark matter. We can try to produce it in colliders. We can do direct searches deep underground, and we can do indirect searches looking for signatures of dark matter out of the sky. And in the end, if we're going to identify something that we see in a collider with the dark matter that we know from gravitational, from gravity is out there, we're going to need the indirect searches to help us with that as well, to make that direct tie between a particle seen in the collider and the astrophysical dark matter. So let me just summarize. We know dark matter exists from its gravitational effects, but we don't yet know what it's made of or what other forces it feels. we think it feels the weak nuclear force. We can look for it through direct production of particles at the Large Hadron Collider, or direct detection experiments deep underground, or indirect detection of radiation coming from dark matter annihilation with a kit. So Veritas and similar telescopes are hard at work looking for radiation signatures from dark matter. Thanks. I'd be happy to take any questions. I'm sorry?
Can we please separate these?
Sure. Yeah. I'll get it.
I think we'll find out what dark matter is made of within 2 lifetimes.
I do. You mean human lifetimes?
Yeah.
Yeah, I do. These direct detection experiments have had a couple of interesting hints in the last couple of years, and it's an area where people are working very hard. They're kind of pushing their technique forward by an order of magnitude of sensitivity every few years. And likewise, the indirect detection techniques are kind of really pushing forward. I think there's a very good chance within 10 years, 15 years, we'll have detected it. Understand all more about it.
But do you think we'll be able to use it? In a sense of maybe not fuel, but maybe creation of other objects that we use?
If so, I think that could easily take several lifetimes. Yeah. We don't really know how to. If it's the best weekly interacting, we don't really know how to work with this.
Has it been identified all the sources where gamma rays can be coming from?
Yeah, there are quite a few other sources the gamma rays come from. Supernova remnants, pulsars, supermassive black holes in the centers of our own galaxy and other galaxies.
Does the black holes, supposedly, do they contain any of the mass that we actually consider is in our galaxy?
Yeah, so at the center of our own galaxy, there's a black hole that weighs about 4 million times the mass of the sun.
Is it possible that dark matter can be found there?
Yes.
Because it seems like black holes seem to be the most mysterious places in our galaxy. So if we can start with that, I think it would be helpful.
Yeah, I think so. That black hole at the center of our galaxy, it's the most massive thing we know of in our galaxy, and yet it's a tiny fraction of the galaxy's mass. I want to say, I forget how much our galaxy weighs, but I think if that black hole is 4 million times, I think the whole galaxy is a trillion times the mass of our sun. So we're not sure to what degree a massive black hole would kind of disrupt the density profile of dark matter. The thinking is that our entire galaxy, the visible stuff, is kind of embedded in this halo of dark matter that's fairly smoothly distributed, but might have subclubs and subfeatures inside of it. And it would be densest near the galactic center, just because that's things will tend to fall in towards the center of the galaxy. And it's possible, it's certainly possible that there would be sort of swirls or eddies in the dark matter density near the black hole, produced by the dark matter moving near the black hole. And I know folks are interested in looking at that kind of signature either on that black hole or other black holes elsewhere in the galaxy.
How many power does it require to power the telescope?
Sorry,
how many voltage of power does it require to power the telescope? Uses it for the analysis.
How much power do we use for the power our telescopes? I don't remember the total number, but I think just the electronics to read off the camera, I think is 30 kilowatts or something. So,
Did you get out from the sun or it's like now you own the day?
we're just on the grid. I'm not sure what produces the power in southern Arizona. But, yeah. The question is that?
I'm sorry.
How can you be sure of the mass and weight of the universe?
The mass and weight of the universe?
Yeah, how can you be sure?
It's a hard problem. weighing things is very hard. I think when it's nearby galaxies, and we can see individual stars moving or clusters of stars moving in them and get a measure of their velocity, then we can use classical mechanics by looking at the velocity and the radius that can tell us the mass enclosed in that radius. And then you can use that kind of relation to get an idea of, okay, if a galaxy is this bright, then here's the total amount of mass it has. And look at the correlation between brightness and mass for nearby galaxies. And then for more distant galaxies, you can try to extend that. Look at how bright they are, and then use that to estimate their mass. So that's a partial answer, but it's kind of outside my field, so I can't give you a complete answer.
But if dark matters, their mass and all their properties is not completely known, how can we really be sure that is actually included in the galaxy's mass? And also, what if dark matter is really not as small as we expect, but actually bigger than what we think of as mass? I mean, has that been cleared that it's actually not bigger?
So, the first indication that there was something awry was that, it looked like there had to be more mass to produce the gravity that was required to make stars move the way they were measured to move. So, given that, the assumption is that dark matter responds to feels a gravitational force. Beyond that, there is a huge uncertainty in what the mass of the particle is. If it falls in this kind of width category, then we can place some very loose bounds on the mass. But there are a lot of possibilities beyond just width. And it could be much lighter than we think. I know there are theories for it being much, much heavier than what I talked about. And if it's some kind of exotic particle that's much, much heavier, I believe a lot of those possibilities have been ruled out by other experiments already, because the Pierre-Roger Observatory measures ultra-high energy cosmic rays.
So you've been able to make something similar to the dark matter in lab?
No, we haven't.
But then you really can't rule it out.
It's hard to prove a negative. So I think until we see it, it's really hard to rule out. There's a lot of models that are hard to rule out until we see something that looks consistent with explaining the dark matter we see. So yeah, we have to keep going.
And also you mentioned something earlier that sounds somewhat similar to the gold foil experiment about it was what? It was 2 slides back. It was like more towards the beginning actually. No, before that. Yes, it was somewhat similar to this.
Yeah.
But even before this, you mentioned how with the lights from the galaxy, there's an outside galaxy and there's a galaxy cluster, and then the lights go around it and not through it. But it's not completely reflected either, like the atom was in the gold foil experiment.